This is Lab 4 Oscillations. My name is Jack. Introduction. The lab setup included a spring, a weight to put on the spring, a person to release and move the weight, a blank background to make the movement easily seen, and a camera to film it. However, we just used the provided video in this case, and the purpose of this experiment was to observe the motion of a mass as it is thrown and moves in oscillation, so we could then compare the observed results with our computational model results to see how they differ, as well as generating energy change graphs of the following. This would be analyzing the physics principles of Newton's second law, all the different kinds of energy and their equations, and Hooke's law, most importantly. Our observed video that we used was this one shown here. I'll play it just in case you haven't seen it. And some key observations to be made is that the camera isn't moving, the object is only moving in two directions. The meter stick isn't shown as a size reference, but we know the distance from the mass to the fixed point is 0.7. And the system is the mass, spring, and the gravitational potential energy for the mass, and the surroundings would be the air around everything, the frame or hook holding the spring, and the earth. The tracker results that I got using the process I described earlier, I tracked it using what is shown here, plotting the position of the mass at each time step to analyze and get data from the video to use for my observed and predicted models, which I will now show, or elaborate on, sorry. The code, we utilize the energy formulas for kinetic energy, 1/2 mv squared, gravitational potential energy, m times position times the force of gravity, and the spring potential energy, which is 1/2 ks squared, and the total energy, which is just adding those all together. As you can see from the code, we compute the forces of gravity downward using Fg equals negative mg, sorry. And the spring force pulling towards the origin using Fs is equal to negative Ks S L hat, and adding them to get the net force. Then we use the position and velocity update formulas, Newton's second law, to use using the values we calculated earlier. And finally, using both the initial and final system energies, we find energy change for gravitational potential, spring potential, and total energy. And the initial values I use for the code are shown up here, and everything else there. The graphic analysis, as you can see from the lines on the graph, the observed y position is a little lower than the computational model, which could be due to some air drag, friction, or issues tracking due to lack of frames. This is the same situation for the x position, but it definitely appears to be a little more accurate, as you can see right there. And looking at the change of the energy graph, you can see how the energy is transferred from spring to gravity potential energy. The delta E stays relatively equal to 0. It moves a little bit, and the kinetic energy diminishes as time goes on, and how it corresponds to the energy exchange between the kinetic and potential as well. And there also could have been some additional variation in the data if the spring wasn't released perfectly in only two directions, which it probably wasn't. This is the video that my code generated. I thought I'd show a little bit of it, but we don't need to see all of it. I just thought I'd show it just in case I needed it. Now for the discussion. The energy principle is indeed satisfied. In the computational model, the total mechanical energy remained nearly constant throughout the simulation, while kinetic, gravitational, and spring potential energies continually exchanged. Their sum stayed the same within small numerical variation. This consistency confirms that the energy principle is satisfied, and energy is conserved within the isolated system. And tiny deviations are likely due to rounding errors in the numerical integration, not a true loss of energy. The oscillation periods obtained from the x and y data were close in value, but not exactly the same. The slight difference occurs because the spring mass motion is two-dimensional, and the horizontal and vertical motions are coupled. As the mass swings sideways, the spring also stretches and compresses, causing small shifts in the period and phase between the two directions. Overall, both motions demonstrate consistent periodic behavior that supports the model's prediction of coupled oscillations in the spring mass system. And for the conclusion, this lab showed that a two-dimensional spring mass system conserves total mechanical energy as kinetic, gravitational, and spring potential energies continuously exchange. The computational model closely matched the experimental data, with small differences caused by air resistance and friction. And overall, the experiment confirmed the energy principle and illustrated how modeling and measurement together reveal the physics of oscillatory motion.